Last class we talked about series and parallel resistors. Let me kind of jump to that there we go. The main points. We talked about current and voltage and how it behaves in a circuit. And there's a few key points. One of them was that current changes at a junction. A junction is where there's more than one path. So say we have a wire coming in and then it's got, who cares how many paths? 10, 20, 2, 3. As long as it's got multiple directions it can go. Say it goes that way, that way, that way. That's a junction. Current is changing, but voltage isn't. As long as you're on a wire, voltage is staying the same. Voltage does change when you hit a resistor or a battery or a capacitor. Okay? So, voltage changes only when you hit a resistor or capacitor or battery. Current changes the second it splits and the path diverges. We talked about series. Series was one path. Let me show a quick picture of that. So series was that one path that you have to get from one place to the other. There you go. One into the battery. There's only one road back home. If that road breaks, you're SOL. Everything turns off, which, is a good thing. If I hit the lights, lots of lights turn off. That's very convenient for us. Parallel circuits have more than one path. In a series circuit, the voltage or the current was also constant. Let's get a better picture parallel. So in a series circuit, the current was constant because there's only one path. Who cares if that path gets narrower or wider? The same amount of current's got to get through it. Parallel voltage was constant because even though there's a bunch of junctions, remember voltage is constant on this side, voltage is constant on this side, on the bottom side. So voltage is constant, but if one of these breaks, the rest can stay on. Has all sorts of useful applications. If I turn off the lights in this room, the rest of the lights in the building stay on. They're in parallel with each other. Okay, so that's a quick summary of what we covered. I did a problem with you all fairly. This one just kind of got us in the idea that basically any time you see a circuit with more than one resistor and it asks you to find anything, the current, the voltage across one of them, the power, whatever, you got to condense it to one resistor and then you kind of work backwards. We're going to explore that today when we're going to do this problem I'm going to show you all right here is classic problem. These problems are going to show up. They're almost a guarantee there's going to be a problem like this. Almost guarantee that one of the free responses will be something like this because these are there's a lot of things, a lot of skills that you're going to be using when solving these. So let's go ahead and jump into this one. We're going to see this one algebraically. It's going to look a little messy, but the concepts are going to work out well. No, this one is harder, so I'll stick with it. Yeah. All right, it says, here's a circuit. I have a 9-volt battery, and we have that going into a 2-ohm resistor, and then the wire splits, goes to 2 other resistors, comes back together, and then rejoins the battery. First thing I want you all to notice is there is both series and parallel in this circuit. This is why this is a good problem. It's going to be utilizing all the skills, series and parallel together. And this problem says, what is the voltage across each resistor? What is the current across each resistor? And so when you see a problem like this, your first thought should be immediately to get the single resistor by itself. It's going to get a little ugly. I'm going to warn you all, it's going to get a little ugly. That's okay. But that's why I picked this one to solve for you all instead of one that's maybe a little bit less ugly. So, just because the variable, you'll see, it'll all be good. All right, so let's go ahead and start to make our end goal is to take this and make it look like this. To take all those resistors and kind of combine them together, and then we can kind of work our way backwards and get that RA. Oh, you know what? What am I saying here? There's an even quicker thing. So, yeah, we are going to ultimately do this, but I'm going to show you all a nice trick. That's silly me. I was going to make my life way harder than I needed to. We're going to be able to get RA right off the bat. We're going to be able to get RA right off the bat. Let me label some things on the circuit for you all, and then I'm going to see if you can figure out why I can get RA really simply. Right off the bat, remember V equals IR. That's just going to get used so much. So we do want to get to one resistor. We're going to need to do that to solve most of these things. But let me just label some things here. Whenever you're doing a problem like this, something you can kind of do, is you can find the current and the voltage in every single one. So I'm just going to kind of jot those down. V1 equals I1 equals, because that's resistor 1. This one's called RA, so I'll call that VA, and I'll call that IA equals. Okay, it's not as nice as I thought. Nope, never mind. No, it is. R4. No, it's not. It's going to be grosser. My apologies. I got all excited for nothing. There is no simple way. We're going to have to work towards this. All right. IA, VA, I4. We're basically going to find all these things. So let's try to get to this R net. And then we're going to kind of work our way backwards, and it's going to be a real good time. All right. So first step when you're doing something like this, when you're combining circuits like this, you want to combine the parallel resistors first. Here, the question is, why do I do that? Why do I combine the parallel ones first? Well, if you look at this picture, there's nothing, so you basically want to combine the ones you can. If you have series together, great, combine those. If you have parallel together, great, combine those. I don't have anything just in series. I've got this one resistor, and technically it's in series with these two together. And I use the word technically because, I mean, it is, but those are in parallel. They're not one resistor. We can't just add all that stuff together. So let's go ahead and combine these two resistors into one resistor. So let's combine those two into one. How do we do that? They're in parallel. So what am I going to call that resistor? I'm going to call it RA4. RA4. Why am I going to call it RA4? Because it's combining A and 4. That's just an easy notation to kind of keep that in mind. How do we combine parallel resistors? 1 over, you know what, let's use the easier one. RA4 is going to equal 1 over RA plus 1 over R4. Okay? And maybe you can start to see why the algebra is going to get a little not ideal. That's okay. 1 over RA plus 1 over R4. Okay? So, how do we get that? Well, we know R4, so we will put that number. So 1 over RA plus 1 over 4, or 1 over 3. We're going to have to do least common denominator. So 1 over 3 plus 3RA equals... No. I'm going to spare you all this. I'm just going to delete this problem. I'm going to make your all's life easier. This has little benefit. I'm going to delete this off the problem set. My apologies, y'all. Let's not make this. This is not worth the time and effort today. So.
Wait, but that's going to be on the next test.
It will not. No. One like this. I'm going to modify this problem on the fly. So my apologies, y'all. Let's make this problem actually not just an algebra exercise and make it a physics exercise. So I still want all those things. Let's change things. And let's just say if if the current through R1 is that, yeah, sure. What is RA? No. What is the voltage in each resistor? What is the current through each resistor? RA equals, pick a number. 3, great number. 3 ohms. All right, great. Okay, this is going to be far more beneficial. My apologies for all that snafu. All right, so RA is now 3 ohms. Wow, we did it. We did all that gross algebra. Good job, us. So RA is now 3 ohms. Now I get to kind of more show off. We still need to get the current and the voltage in each resistor. And again, I'll go back, I'll look at the problem set, I'll modify it as needs be. Don't worry, one like this isn't going to show up on your problem set on the quiz. We are still going to want to get to one final resistor. And now, without having to avoid all that grossness, we can see how we're going to do that. So let's get that RA4 again. Let's take this, and we are going to make that in one resistor. I'm going to basically rewrite everything I just wrote, but now we got the numbers. 1 over RA plus 1 over R4. So 1 over 3 plus 1 over 3 equals 1 over 2 over 3. And, honestly, you could just plug that into your calculator, but you all did pick a nice one. Nice little number there. 1.5 ohms. All right, great. So that's our RA4. And I'm going to draw a bunch of pictures. Every time I combine some resistors, I'm going to draw a new circuit. I'll move to the next slide in a second, but I'll leave this for now. You may not understand why I'm combining these resistors all together, but you will see when we work backwards the necessity of this. So for now, just trust me that when you're given a circuit like this, and I'll just tell you, you're going to have the resistors will be much nicer for you. When you're given a circuit like this, you need to get to a circuit with one resistor. Just trust me on that. When you see that, just like when I told you all, when you see the word speed in a problem, think conservation of energy. When you see a circuit that looks like this, get to one resistor. Keep that mantra in your head. That'll get you there. All right, so let's go ahead and copy that problem over. Let's copy that circuit over. And we are going to slowly combine the elements together until we have a nice, beautiful picture. So here's what we started with. We need to find the voltage and the current in each one of these resistors. So we took this circuit, and so far we have condensed those two ones in parallel. So here's my R1. That's still up here. We haven't done anything with that. But we have condensed those two over there into RA4, and we calculated that as 1.5 ohms. This one is still 2 ohms. Okay. So again, just stick with me, trust, and we need to now combine these. Why? You will see when we work backwards. So, look at this for a second and see, is that series or parallel? It is series, so we're going to use our rule for series to combine that. We combine the parallel because we could. Now we got the series. We can combine those because we're allowed to. If you have resistors that are in series with each other, you're allowed to combine them. If you have resistors that are in parallel with each other, you're allowed to combine them. If you have some combination, go to the simplest element. The simplest element we had in the beginning was the ones in parallel. All right, so great. We are going to combine them into one resistor. We'll call that R1A4. I'm literally just putting all the little numbers and letters next to each other, just to note it's the combination. So how do I get R1A4? Well, that's going to be R1 plus RA4. R1 plus RA4. We just add them in series. Nice and easy. 2 plus 1.5 equals 3.5 ohms. Spot on. All right, and we still have our 9-volt battery. Now we're going to start to see the magic of why did we do this? Why did we get R1A4? Nowhere in the problem did it say find the net resistance of the whole circuit, and yet we have to do it to work backwards. So, here is why. I have one resistor and one battery, so I can use our favorite equation, V equals IR. The voltage of this will be the voltage of the battery. The voltage of 1A4 is the voltage of the battery because it's the only thing in the circuit. Remember, voltage is a difference, so the voltage across this is the voltage across the battery. Just depends on which way you look at it, but you see the voltage of the resistor is the voltage of the battery. V equals IR, so if I want to solve for I, so V equals IR. If I want to solve for I is going to be V over R. So I equals 9 over 3.5. And I can get the current through R1A4. And once we get that, I want you all to think which of these values is useful for us? Is it the voltage or the current? Which is the one that's going to allow us to work backwards and start to find some values for the rest of the resistors? So we get 2.57 amps. So we started with a circuit that had 3 resistors in some weird combination. It was like there was a resistor here in series and 2 that were in parallel. We combined the ones in parallel, and we got 2 resistors that were in series. We combined those to get this final resistor. We are now going to work backwards. So we go back to this circuit, and that circuit was in series. What do we know about resistors in series? Think about that. What is constant? Is it voltage or current? It is current. You know the current through R1A4, which means you now know the current through R1 and RA4. Current is constant in series. Current is constant in series. So when we work backwards, therefore, I haven't used this symbol much in this class, but those 3 dots mean therefore, simpler than writing therefore. R1A, the current through 1A4 equals the current through resistor 1 equals the current through resistor A4. I'm referencing that last step before that. All of them have the same current. And now that I have the current for R1 and RA4, let's just kind of jot those numbers down. We know, again, I'm gonna end up using a lot of space here. Now that I know the current in those, just kind of jot this down here. No, let's put it right here. We got a little space. IA4 equals 2.57. And where do I want to put that? Yeah, that's fine. R1 equal 2 ohms. We'll just put this off to the side. I1 equals 2.57. Oh, look at that. I've got resistance. I've got current. If only I had some handy equation that related current, resistance, and voltage. You can start to see why we have to kind of do this whole process. So, VA4, so V equals IR, so that's going to equal IA4 times RA4. Again, this notation may look a little silly, but it does help you keep track of things. So V1 equals I1 times R1. Just plug in the numbers. So the voltage across A4 is that 2.57 times that 1.5. That V1 is going to equal that 2.57 times 2. And that gives me the voltage across each one. So we already got, for resistor 1, we'll be done after this step. Resistor 1, we have everything now. We still need to go and get RA and R4, but we are very close to that. So that one's got 3.855 volts. And the one down here, 2.57 times 2, equals 5.14 volts. Now, there's a little bit of rounding, but I do want to point out something to you all while we kind of pause here. We just got the voltage of each of those. You add those two numbers, you get a number that should look very similar to another number in our problem. 3.855 plus 5.14. You add that up, you get 9. There was some rounding that makes it off by, a couple decimal places. But you get 9, which makes sense. The voltage drop across this one, and the voltage drop across this one, get you the total voltage of the battery. This is a great way to check your work as you're kind of going through problems. Do you remember these nice little rules? Okay, so, I'll put those numbers up here. A4 is 3.855 volts. I'll be a good physicist and make certain I put my units there, even if it's a pain, because I don't have space. All right, and I know I'm spending a good amount of time on this problem. We'll still get through the rest of the stuff. We don't actually have that much more to cover in the rest of these slides. But I'm spending the time because these problems have so many steps to them. Once you've done a couple of them, you'll get the hang of it. And again, I'll look through it and double check to make sure I don't have any weird ones like that one again. The one that was there and I magically fixed. All right, so let's draw our circuit. So we have R1 here and we have RA4. So R1, we just got everything for that. We have RA4, we just got everything for that. We now need to go back a step. Again, we're going backwards. And we have a resistor, two resistors in parallel. How do I know they're in parallel? They share a wire on each side. So this was RA, this was R4. I want you all to think, we just got everything. So let's go back to our picture here. We just got everything for both of these. RA4, we are splitting up back into RA and back into R4. What stays constant? In parallel, what stays constant? I'll give you all a few seconds to think about it. In series, it was current. Process of elimination. Yeah, it's voltage. So look at that. You got the voltage of A and you got the voltage of 4. You have the resistance of A, you have the resistance of 4, you have the voltage of A, you have the voltage of 4. Let's go ahead and kind of put that on here. You have the voltage of A4. Did I break everything? No. You have the voltage of A4 here. You have the current of A4. V voltage in parallel is constant. So when we go backwards, therefore, the voltage in A4 equals the voltage in A equals the voltage in 4. The voltage across this resistor is the same as the voltage here and the voltage here. You got V? You got R. Now we can get I. So we said that VA4 equaled, we just calculated that, 3.855. So RA equals, we said 3 ohms, and this is going to kind of be a little silly, but that's fine. IA equals, we got to find that. Let's just put the V first, because we know that one. VA equals 3.855. So I need to get the current. How do I get the current? V equals IR. I equals V over R. You know V, you know R. And we're going to repeat that same thing for R4. But here's where it gets a little silly. Unfortunately, fortunately, it depends on your perspective. The resistance is the exact same value. The voltage is the exact same value. So when we plug in the numbers, it's going to be the same thing. So once we get the current in A, it ends up being the exact same because the resistances were the exact same. That's not always going to be true. Symmetry. You know, if they're both the same resistor, you're going to get the same current. Yeah.
So when we have like a problem like this with two parallels
Mm-hmm.
in series, isn't it really just always in series in the grand scheme of things, and you can just combine parallels all the time?
You can combine like elements. It's kind of like when you're doing a math problem. If you kind of have some addition off by itself, you can kind of combine those. If you have some multiplication off by itself, you can combine those. The same thing here. We couldn't do the series addition until we combine these first. Nothing in this circuit is in series. There's no two resistors in series right now. So therefore we can't combine any in series. There are two resistors in parallel, so we can combine those. Basically, you combine what is possible. You combine what is possible, and then you go to the next step, combine what's possible, next step, combine what's possible, until you finally get to...
Are we considering it a series after we combine them?
Yes, you're considering a series after you kind of combine them. Yeah, just to make it easier to kind of work through, we'll use that logic. We'll use that idea. So let's quickly get a number here. 3.855 divided by 3. That's going to equal something bigger than 1. 1.285. It so happens to be that both of them get the same current only because the numbers are identical. If we had chosen the resistance for A to be anything else, then the currents would not have been the same. But they are the same because the resistances were the same. Anyway, I hope you all kind of got the idea that you combine everything down and then you kind of split it all up. I will probably sometime next week, maybe just throw out a few problems and just kind of have you all think through what would you combine. That would be a good practice. Not necessarily doing the math, but hey, which resistor should I combine first? Then which resistor should I combine after that? Good news for you all on the problem set in the quiz. They're all, let's just go ahead and jump to the problem set. The problem set I gave you all, they all look like this circuit. So again, I'm going to look through those tonight just because clearly I gave you one that was absolutely disgusting. So I'll make certain there isn't any other disgusting ones like that. I do have you find R1 here. I'm kind of okay with that. This is one which is more matches what we just did. I'll just straight up delete this bottom one here. So, okay. Yeah, I'll explore number 9 on there just to make certain it's not too bad. So there you go. And next week, so the quiz, you can't expect anything more complicated than this. But next week I do want to kind of practice some, hey, what should I combine first? Because that's a skill that if they all look the same, you kind of have a straight up idea, but I want to give you more than that. Okay, so let's move on to some new stuff. So we just did resistors. Great. Resistors, woo, good job us. We've learned how to kind of combine them. We've learned that current's constant. We've learned that voltage is constant parallel. On to capacitors. These are going to be a little simpler. You're not going to be involving some crazy circuit. Like, you're not going to necessarily have to do the same. Maybe. You may have to combine some capacitors together, so you may still need that skill set of which ones are in series, which ones are in parallel. We'll do a little bit more practice with that on next class. But for now, let's just get into how do you combine them. Capacitors, instead of current being constant, charge is constant. Instead of current being constant, charge is constant in series. In parallel, great, voltage is still constant for the exact same logic. So, when capacitors are in a line with each other, aka series, there's no junctions, charge is constant. When the capacitors share the same wire on both sides, I want to use the word wire here instead of just junction. In fact, I'm going to even change that. When they share the same wire on both sides, I'll try to use that terminology more, they have the same, they're in parallel, and the voltage is constant. I consider this all just kind of like one wire, even if that wire splits up. So voltage is constant, there's not much we need to talk about there. That's the same exact logic. The voltage on this side, there's nothing changing it, so this side has some voltage, call it V1, or call it VA, and then the other side has some voltage, call it VB. You can see, if I want the voltage across capacitor 1, VB minus VA. If I want the voltage across capacitor 2, VB minus VA. Same voltage difference. Why is the charge constant? That's kind of a fun one to think about a bit. Capacitors store charge. Remember, that's their goal. They're basically just buckets for charge. They store charge in a circuit that has all sorts of applications. You all can maybe do your physics about that. Lets you store charge in one place. Think of like a bucket. Why is a bucket useful? Why would you want to pour a bunch of water in a bucket as opposed to just getting it out of a hose? Well, if I need a whole bunch of water really quickly, a hose only goes so fast. But if I have a bucket, I can dump that bucket and get a lot of charge really quickly. I can get a lot of water really quickly. Capacitor is the same idea. I can store up some charge. If I need a bunch of charge really quickly, discharge them, and you're releasing all that charge in a very short period of time, just like dumping a bucket lets you release a bunch of water in a quick period of time. Why would you want that? Defibrillators. If you all have ever used those old school cameras, where you like do that little, like the manual ones, the temporary ones that you throw away and that's got that little switch on it, you hit it and it goes, ee, and it makes that charging noise, and then the light blinks. That is charging a capacitor. When you hit the button, it releases all the charge and the light goes flash. I haven't seen that movie. I hate horror movies. They're the worst. I'll trust it's in there though. So they charge them up, and remember, one side is positive, one side's negative. So let's just call this side positive. So this has positive Q on it. And by definition, the other side is negative. Now, let me flip those. Let me flip those to make the example. Because we said negative is the one that's moving. It doesn't really matter, but I think it's going to make it easier. So I charge it up with electrons. Remember, electrons are the ones moving. I charge up the side with negative charges. What's that going to do to all the negative charges on the other plate? Like charges repel. So it's going to push away those negative charges, thereby making the side positive. Where did the negative charges go? Right here. They only have one place they can go. There's a gap. They can't fly through the air. So this builds up with all those extra negatives. Well, what do those negatives do to this side? They push away the charge. Look at that. So that's the logic here. This side builds up with negative charge, pushes away electrons. They only have one place they can go. They can't escape. So they build up on here. That pushes away these ones. There you go. That's the derivation for why charge is constant. That's the logic. Why charge is constant. You don't need to remember that. If you could just remember charge is constant in series, you're good to go. But for those that are curious. So, how do I add capacitors in series? You aren't going to like this. It's the exact opposite of resistors. Take the rules for resistors and flip them. So, to get the net capacitance in series, this is going to look like the equation, and let me rewrite this for you all so it kind of looks like the one we saw before. If you want the net capacitance, it's 1 over C1 plus 1 over C2 plus 1 over ... however many you have. The rules for capacitors are exactly opposite the rules for resistors. The rules for capacitors are exactly opposite the rules for resistors. It comes from the equation C equals Q over V. Charge is constant, the charge cancels out. Due to a little bit of time constraints today, I'm not going to spend too much time on that. But it comes from that and just due to where the variables end up placing. So the derivation, C equals Q over V. And when we say charge is constant, it ends up canceling out and gets you there. So if you want to get the net capacitance and they're in series with each other, you got to do the gross math. In parallel, resistors in parallel have the gross one, capacitors in series have the gross one. They're opposites. Just remember kind of resistors and capacitors opposites. If you can remember that, that may help you. However many you have, you got to do this. Same thing with resistors. All I did, in case you all aren't clear what the heck I did in that arrow to the top right, this is 1 over C net equals all this. If I just want C net, I need to do 1 over all of this. I just saved you all an algebra step. Saved you all an algebra step. If you just want C net, 1 over C1 plus 1 over C2 plus 1 over C3, so on and so forth. And how do I make certain this makes any sense? Practice. What's the net capacitance? Oh, and the same rule applies. In series, when we had this gross thing for resistors, when we had this gross equation for in parallel, the net capacitance will be lower than the smallest capacitor. That same rule is going to hold here. So anyway, we got 0.1 microfarads, 0.2 microfarads, 0.3 microfarads. They're all in series with each other. They're hooked up to a 12-volt battery. So if you want, there we go. Now it maybe looks like a more traditional circuit, but they are in series with each other. This is honestly just kind of practicing using that equation. And how confident are you? The rounding here is technically a little off, but that's okay. The answer, the rounding's a little off, but it gets you there. Just practicing putting this in your calculator. How do you all know how to use that equation I just showed you? So try it out, plug it on in. Looking pretty good, y'all. And these are not resistors, so we have to use our new rule. So capacitors in series, we add differently than resistors in series. And we just saw that equation. All right, I'm going to go till 2:15. And 5, 4, 3, 2, 1. All right, so let's go ahead and solve this out, and then we'll pick the right answer. So net capacitance, we are taking this and we are making it into one capacitor. This is what a capacitor looks like. It's just 2 plates. It looks different than a battery. A battery has one long end and one short end. We make that a little bigger, easier to see. A battery's got one long end and one short end to denote a positive and a negative end. A capacitor is just those 2 plates, because that's what a capacitor is. It's 2 plates. So, in series, which this is, because there's only one path, the net capacitance is 1 over C1 plus 1 over C2 plus 1 over C3. I am not going to convert my units because my final answers are in microfarads. So if I convert them, then I'd have to convert back. So I'm just going to leave them in terms of microfarads since that's what the answers are in. So 1 over 0.1 plus 1 over 0.2 plus 1 over 0.3. And I just plug this whole thing into my calculator. I don't solve the bottom and then do 1 over it. This is the benefit of having one equation. If you're just careful, you can plug it all in one go. 1 divided by parentheses 1 over 0.1 plus 1 over 0.3. And you get 0.0545 microfarads. Again, that's where I told you all. technically, it probably should be 0.055. You know what? There you go. But it was the only answer close to that. And it is smaller than the smallest capacitor. There was 2 answers that were smaller than the smallest capacitor, but only 1 right answer. All right. So, in parallel, we get a nice, easy equation. Oh, I guess I should point this out. If you picked this top one, that means you just added them. You don't just add them in series, but in parallel you do. In parallel, capacitors just add. It's the opposite of resistors. The rules here are the opposites of resistors. Capacitors and resistors have opposite equations. Just try to tuck that somewhere in the back of your mind. So it's really nice and easy when they're in parallel. And this one, I don't need any math to help you understand why this is, which is kind of nice. So capacitors in parallel just get added. And here's the trick to understanding why that is. Think, what is capacitance? Capacitance is how much charge they can store per unit voltage. Well, they all get the same voltage. So effectively, when we are combining these into one capacitor, you are literally just, imagine I took these and I just connected them all together. Ta-da! So you just add them. It's a kind of a silly explanation, but that's the idea. They all get the same voltage, so this one, it's like this one can hold a certain amount, this one holds a certain amount, this one holds a, so they just add really nicely. In series, it was a little bit more complicated because they didn't have the same voltage, so that threw things off, but here you just kind of can connect the plates. Ta-da, add up the areas, add up the distances, they have the same voltage, bam. That's why you just add them up. It's kind of silly, but at the end of the day, you just need to know that in parallel, they just add up real nice. So, yeah. It's a good question. So we're adding up numbers here, and they'll never be negative, so it'll always be larger. Yep, when you're just adding the numbers, it'll always be larger. When you're adding the inverses, it'll always be smaller. It's a great question. And I wrote the wrong answer here, didn't I? That's why you were asking. I was like, CNET will always be bigger than the smallest C. You know what? Bigger than the biggest C. It'll be bigger than all of them. Yeah, thank you for that. Thank you. Typos happen to us all. Yes? Nah. So I fixed it at some point and then ruined everything. Yep. Goodbye. There we go. Thank you. I appreciate that. So Pass Me did fix it. I just didn't delete my mistake. All right. Why do they add? Just make it into one big capacitor. Look, Pass Me, Current Me. We're doing a good job. All right. So there you go. Circuit. They are in parallel. They are connected to a 12-volt battery. What is the net capacitance? The answers are the same as the last. The answer choices are the same as the last one. 0.6 microfarad, 0.35 microfarad, 0.054 microfarad, 0.006 microfarad. All right, we won't get some of these people. The nice thing is, this is math you can do in your head. It's my hint to you. So, it's always good to use a calculator. It never hurts to use a calculator, double check. I do that more often than probably care to admit. All right, we'll go to 115. In 5, 4, 3, 2, 1. These are in parallel. They follow the opposite rule of resistors. They just add C1 plus C2 plus C3. 0.1 plus 0.2 plus 0.3, 0.6. Bam. Because my answer was in terms of microfarad, I purposely try to keep these clicker questions quicker. I'm not trying to do any crazy unit conversions in them. All right, and mark this now so I don't have to later. Great job. Okay, so in summary, they're opposites. Series, add them up for resistors. Capacitors in parallel, add them up. Series and parallel, it's the inverses. Capacitors and, resistors in parallel, inverses. Capacitors in series, inverses. And to remind you all, I'll just kind of jot these down. The way that these are currently written is kind of like the normal way you'll see in any physics textbook, but I've realized when teaching my high school physics class, while that may be kind of nice for derivations, at the end of the day, why do algebra? Why have to try to remember to do that 1 over? Why risk it? I'll just give you all, hey, R net is 1 over, all that stuff. No reason to do that algebra every single time and have to remember that. I'll just straight up give you the equation that's this. Doesn't take me too much extra work. But the reason it's in that original form comes from the derivation. The reason they keep it in that 1 over R, the reason they keep it in that 1 over C is from the derivation. But anytime you look it up online, it'll basically be that way. All right. So, this is a good problem for us to practice that idea of series and parallel. Practicing the same kind of tactics we'll use for which do we combine first, apply with capacitors and resistors. So this problem says find the total capacitance of this combination of series and parallel circuits if they're connected to a series and parallel capacitors. If they're connected to a 9-volt battery, what is the voltage and charge on each capacitor? This problem is almost identical to the resistor one, but I replaced all the resistors with capacitors, and the numbers are different. And instead of finding current and charge, or current and voltage, you're finding voltage and charge. Something I do want to note to you all that I haven't really mentioned, in a circuit with capacitors, the current will be 0. Because once these capacitors are charged, if the current wasn't 0, that would mean they keep charging. So the current goes from 0 and it kind of builds up and it charges them, but at some point the current stops because they're completely charged. That's why you're never going to solve for current in a problem like this. So let's go ahead, hey, you want a battery on this? Bam, there's the battery. Who cares how ugly my wires are? It says it's connected to a battery. There it is. Now it's connected to a battery. So, I want you all first step off the bat. Think in your head, which capacitor should I combine first? Should I combine 1 and 2? Should I combine 2 and 3? Should I combine 1 and 3? Is there somehow some way to combine all of them in one step? Think about it. This will be kind of good practice in the first one. So it's the same problem as the last one. So when you're looking at a circuit like this, basically your mind should say, what can I combine? If there's any purely in series with each other, great, you can combine those. If you have any purely in parallel with each other, great, you can combine those. Let's just give it a quick example. Say there was another capacitor here. I am 100% allowed. I can do either one first. I can combine these two first, or I can combine these two first. These are purely in series with each other. These are purely in parallel with each other. So it would not matter the order that you did it in. Let's do another hypothetical. Let's say there was a capacitor in this branch right here. Clearly there's not, but let's imagine there was. If there was, I can't do parallel first because there's nothing purely in parallel in this circuit. First, you need to combine these ones, then you would combine these ones, then you would combine everything. You got to look for the ones that are either purely in series or purely in parallel. If you have a choice, it doesn't matter what you start with. Okay? Again, next class I'll try to get some clicker questions for that. Unfortunately, I don't have any in this slide. So, let's go ahead and solve this. First step, find the total capacitance. Why do we need to do that? For the same reason that we did it for the resistors. Just trust me, when you have a circuit like this, one, it tells you, that's kind of nice. But we would need to do that anyway to work our way backwards. So at the end of the day, we need to get this from a bunch of them to one of them. And you all were already spot on that we are going to start with the parallel first. So, we are going to combine those. So our first step will be taking this circuit from, and I'm not going to even draw the battery. I'll draw the battery. We're going to get it to this. Where I am making C1, 2. I'm combining 1 and 2. So I call it C1, 2. Just, in my opinion, that's nice, convenient notation. So how do I do that? They're in parallel. We like parallel capacitors. C1, 2 are in parallel, so therefore I just add them. So 5C1 plus C2, because they're in parallel, equals 5 microfarad, 5 plus 2, 7 microfarad. If I wanted to, I could convert it to regular farads. I'm going to save myself a few letters and just do that later. Let's just keep it in microfarads for now. Yes, when we plug them into equations, we'll need to do that, but I'm just saving myself some writing. Okay, we got that one down here. Now they're in series. So, and I'll parallel. Bam. Now I need to combine C12 and C13, or C12, and I'm just going to draw that here. So I'm going to take my battery, and I'm going to combine those into one capacitor. We'll call that C123. These are in parallel. They're in series. So C123 will be 1 over C12 plus 1 over C3. Capacitors in series add grossly. And that's going to equal 1 over 7 plus 1 over 3, which comes out to a number. Probably not a nice one at that. But the world doesn't use nice. Oh, okay, that's not bad actually. 2.1, which is smaller than the smallest one. 2.1 is smaller than 3. It's good to kind of have that check. Microfarad. Great. Okay. So, we have our capacitance right here. We have this capacitor. Why did we get that? Well, the same rule we use for the battery, for the series. The voltage of the battery will be the voltage of this. When you get down to one element, the voltage of the battery, which in this case is 9 volts, is going to be the voltage of the capacitor. Okay? You know C, you know V. Do you remember the equation from capacitors? We can get Q. C equals Q over V. I'm going to move on to another slide just so we can do that, have space for it. So I'm just going to copy this over. Wait a few moments in case anyone's jotting down the extra stuff. We're going to be able to get the charge, and then you all can go ahead and start thinking one step ahead. When I go backwards, what is constant in series? What is constant in series for capacitors? And it's the same logic. Yes, sir. It is charge. So once we get charge for this one, so let's go ahead and get all the values. We'll be able to take that charge and move it backwards. All right, so C123 equal 2.1 microfarads. At this point, since we're going to start to use equations, I am going to put it in terms of the scientific notation. And we need Q of 1, 2, 3. C equals Q over V, therefore Q equals C times V. Just multiply that V on over. So Q123 is going to be 2.1 e to the minus 6 times 9. Which is a tiny number, which makes sense. We started with tiny numbers. 1.89 times 10 to the minus 5. This will be good review. If you remember what unit goes after charge. If you remembered coulombs, you did a good job. Which is a little unfortunate because coulombs uses C and capacitance uses C. You got to be careful. There's nothing I can do about that. I didn't choose these things. All right, coulombs. So now we go backwards. We go backwards from that one to the one where they're in series with each other. And yes, in series, charge is constant. So we're going backwards. We put that star in. I'll put it off to the side so I have room because I'm going to need it. In series, Q is constant for capacitors. In series, current was constant for resistors. In series, Q is constant for capacitors. It's kind of nice because current is just moving charge, so that can help you maybe remember those two together. If you remember one, you may be able to remember the other. Otherwise, you'll have it on your cheat sheet. Okay. So, we want, what was these called? V1, C12 and C1 and C3. So C12 equals V12 equals, and Q12 equals, give myself a little bit more room. C3 equals, V13 equals, Q13 equals. Yes, it is a bit of a slog in doing and having to calculate all these things, but once you've done it a few times, it's much quicker. Again, I take kind of longer just because I'm trying to go slow, but as you kind of have done a few of these, it'll get quicker and quicker, and you'll all be on point. All right, so C12, I'm reminding myself, was 7e to the minus 6. Q is going to be the same for both of them, 1.89 e to the minus 5 coulombs, 1.89 e to the minus 5 coulombs. Again, I'm just jumping back and forth to get the numbers. C3 was 3e to the minus 6. How do we get V? C equals Q over V, therefore V equals Q over C. It's just some quick algebra. You can double check that yourself later if you would like. V goes the other side, C gets divided over. So V is going to equal 1.89 e to the minus 5 divided by 7e to the minus 6. The V on the bottom is going to be 1.89 e to the minus 5 divided by 3e to the minus 6 equals. And again, we just have to keep working our way back so we can get all these values for all the things. But at least the numbers come out nice. This one's 2.7 volts. And we'll be able to check our work. You'll see how in just a second. See if I made a blunder somewhere. But it looks like I did good. How do I know that? Remember our rule of voltages. If we start with, if this is a 9 voltage drop, the voltage across both of these together should be 9 voltage, or 9 volts. 6.3 plus 2.7 equals 9. It's always nice when things work out. Makes you feel good about yourself. All right. Now, we got to get work backwards to that C12. That's the last one we have to break up. Same thing, remind yourself, spend a few seconds, what state. We are going from, let me copy this, new slide again, because that's how these things go. These problems just take a bunch of paper. Don't worry, I'll jump back in a second just so in case you're all copying things down. I don't want to, I know there's a lot to copy down here. We are jumping back. The C12 is going to get split into two that are in parallel. So what is constant in parallel? C12 is going to get split back into those two that are in parallel. What is constant in parallel? And the answer to this is true of resistors and capacitors. Anything in parallel, any capacitors, resistors, turns out there's more things to that you can put in a circuit, but for our case, that's it. Anything in parallel, this is always going to be constant. If you thought voltage, good job. If you didn't think voltage, that's okay. That's why we study. I just introduced it to you. Well, we've been saying it for a little bit. But we are going to take this C12, C3, and we are going to split up that C12 back to our OG equate circuit where I have my C1, C2, and we already did all the things for C3. So C1, V1, Q1, I got to get all of those, and then we'll do it over here, C2, V2, Q2. So in our original circuit, I don't have a great memory, 5 microfarads, 5e to the minus 6, I don't want to have to write that again. C2 was 2 microfarads. The voltage, let's put that little star. Voltage is constant in parallel. Voltage is constant in parallel. So we can take our voltage from the last one, V12, 2.7 volts. So V12 equals V1 equals V2. So 2.7 volts, 2.7 volts. C equals Q over V, Q equals CV. So we're going to multiply those out. And boom. If you all are looking at all this and like, man, what a slog. What, so many steps. You'll have a lot more sympathy for electrical engineers. Electrical engineering, I believe, I've heard this from people. You can fact check it yourself. I've heard that it's the hardest engineering major. Certainly, there's a lot of algebra in it, clearly. And this isn't even the worst of it. So, count your lucky stars that you're not, appreciate those electrical engineers out there that are doing a lot of this. They set up a lot of systems of equations. There's something that we're not doing in this class because it's a lot of algebra called Kirchhoff's laws. Look it up in your own time if you want to. But basically set up a bunch of equations. You have mini equations and you have to keep plugging equations into equations, and oh, it's a slog. Very useful, extremely useful. And you all have all the content knowledge necessary to do it, but it's an algebra slog, so I'm not going to spend the time on it because it offers little conceptual benefit for a lot of work. All right, so there you go. We got everything. We have the charge, voltage, and capacitance of every single capacitor in the circuit. Yay, us. Good job, us. There's no shortcuts here, y'all. Sorry. You have to go down to the original and then work your way back. That's just how it goes. If there's a quicker way to do it, I don't know it. All right. So, nice. That kind of closes us out. RC circuits, I'm going to mention this. There's no questions on this. So I told you all, we have 9 minutes, and I'm not going to finish early because that'd be rude to you all who are spending money. But RC circuits is where you have a resistor and a capacitor together. I am not asking you all questions about RC circuits, okay? So there's not going to be any math questions, but this is still important to mention. I told you all that capacitors, at some point the current is 0. Well, why is that? Here is a classic circuit. Imagine this is that little flip thing on your camera, that fake camera. Imagine this is your light bulb right here. There you go. There's a light bulb. This is an example of what a circuit would look like for that. You flip it to switch A. At that time, you start charging your capacitor. That capacitor builds up with charge. As it builds up with charge, it's going to start opposing. So this side becomes positive. This side becomes negative. Remember, current is positive charge moving. It's not the reality, but it's what we define it as. As this charge tries to build, as this current builds us up, at some point it wants a positive charge here. As time goes on, that's going to repel, and it's not going to want any extra. At some point, it's going to get too full. Imagine blowing up a balloon. At some point, you put so much pressure into it, and it's going to push back, and it's too hard to blow it up anymore. Or like blowing up a tire. So eventually, that current will go down and down and down until your capacitor is completely filled. This isn't a matter, it's very quick, milliseconds. Then, what I can do is once I've charged it, I can flip this switch from the charging case to the discharging case, disconnect it from the battery. The battery was the thing holding all that charge in there. The second you remove that battery, remove it, you basically, when you switch it to flip here, it basically pretends like that battery is no longer there because it's an open circuit. That capacitor will discharge very quickly. It'll release all that charge in this circuit, and the current will actually flow backwards, and when everything is here, will experience that current and light up, or whatever else it may be. So you charge it up, and then you have a discharging case. And let me show you all the graphs for that. So it has all sorts of uses, tons and tons and tons and tons of uses. If this was a calculus-based course for your engineering majors, I would certainly need to spend time on it. There's the equation. It looks worse than it is. This is basically kind of an exponential decay curve. You can see that. This one mainly. If you all have ever looked at, what's the half-life of a half-life of any kind of atom or population decay. That's kind of a classic problem you may have seen. You may have seen this. This is an exponential decay. You all do not need to know this. This is just funsies. That exponential decay is there, and this is the charging case. Basically, if you flip it, you get the other one. You can kind of see that. If you flip them, you kind of get that. But the current, you can see here, if we zoom in on my graphs, which are really itty-bitty, you can see here that the charge, as time goes on, builds up, and it gets to a maximum. The current decreases with time, and eventually it goes to 0. The voltage increases, and then the voltage decreases. So, I wanted to kind of show you all this just because I think it is important. This is the discharging case. Again, I have these problems on here. That's okay. We'll maybe kind of do this next on Tuesday or something, do some extra practice problems, because these problems are trickier. Look at that one. Isn't that fun? This will be a good practice for us if you all want to look at this. You know what? Let's just look at this real quick. I'm not going to solve it. This is a good problem. We'll work through this next time as good practice. What would you combine first? What would you combine first? Remember the trick to that. What is purely in series or what is purely in parallel? This looks messy. Just look for it. Where do you have any that are one after the other? If so, great, they're purely in series. Do you have any that share a wire the same wire before and after them? Great, those are in parallel. So spend a few seconds. What would you do first? If you can make the first step correctly, every step after that, I think you'll also do correctly as well. Fun fact, there's 2 choices here of what you could do first. You could either combine these ones first. Those are purely in series. They are one after the other. You're allowed. They're one after the other. Those are purely in series. You can combine those or/and. These are purely in parallel. And you can combine those. Once you combine these, I have one capacitor here. Once you combine these, you have one capacitor here, and we kind of move on to the next steps. So you can do each of those. So that's then going to look like this. We're going to do this next class because I think this is a good exercise. Boom, boom. And then this one over here. I've got this. Now what would you all combine? After you combined those two, what would you combine now? What is purely in series or what is purely in parallel? Is there one in series where it's one after the other? Or is there one in parallel where they share the same wire on both sides? If you identified that these are purely in series, kudos. That would be the next step. If not, that's okay. I'll throw out a few more of these next time we'll practice that. You would combine those, and just for the sake of space and time, I would combine those and it would become this. And now, those are all purely in parallel with each other, and that would be the last step. Okay? Yeah?
Are you allowed to use the 1.5 micro, or 1.5 and the 0.75?
Are you allowed to combine those? You unfortunately aren't, because they're not purely in series because there's a junction between them. And they're not purely in parallel because they don't share the same wire. If there's a junction between them where the wire splits, they're not in series. That's a good point actually that I was able to make because of that question. So nice work. So yeah, we'll explore that. I'll give more hypotheticals on that. We're not going to do this one because that's not something I'm testing you on. So I'll try to give more examples like this where we're not going to even actually maybe solve it all, but I'll throw out some few quicker questions. They'll be quick and easy. Next time we're going to talk about magnetic fields. So today we kind of talked about how to combine stuff together and then work our way backwards. We talked about capacitors in series and parallel. Next time we're jumping to the next big topic, magnetic fields. What makes them and what do they affect? What forces do they cause? We'll be starting with, I believe, the forces they cause, and then we'll see what causes them after that.
Are those kinds of DC circuit functions going to show up as